Okay, so this week I thought we'd do the object model because I've been mentioning objects quite a bit and realised that apart from the initial lecture of 3 slides, hadn't really explained the object model to you in any way, so I thought I'd just bring it forward a couple of weeks. And the other reason I brought it forward was several times I've mentioned the OGC Simple Features model, which is an object-oriented data model, the object-oriented data model that underlies PostGIS geometries and other geometric models in various bits of software. So I thought it was opportune to doing the object model would give an opportunity to explore a little bit more detail what this simple features model is. So that's the reason. So 4 topics here: real-world objects, object concepts, the sort of theory of object-oriented design. We've met UML previously briefly, but another return, a bit more detail to see UML. And then, as I say, once we've seen UML, we'll look at the UML diagram of the OGC Simple Features model. So that's our schedule. So, first of all, just a little brain exercise here. What objects can you see in that picture? Shout them out. A statue. Plants. What? Buildings, yeah. Lampposts, yeah. Bollards, yeah. Bollards, in case anybody doesn't know what a bollard is. Anything else? Flagpole. Flagpoles? Oh, yeah, flagpoles, yeah. Streets, yeah. People, yes. Shops, yes. Banks, yes. All right, okay. Lots and lots of things that we identify as human beings as objects. Just to pick up on 2 of them that were mentioned, buildings and shops and banks. Clearly those are, we know what a building is, we know what a shop is, and we know what a bank is. But clearly they're different types of objects in that one relates to a physical building, and the other thing relates to the function that goes on in it. So different viewpoints on the town centre, one functional, the other physically based. All right, so we can divide the world into classes of things and instances of things. I don't know which is the best way to go around that. So in object-oriented parlance, in the object-oriented model, we think about instances which are individual physical or abstract things. Here is a tree, one of the ancient yews, one of the very old yew trees, about 2,500 years old, called the Faltingal oak. Oh, sorry, yew, not that it matters. But it's an example of an actual physical thing, a yew tree, a particular yew tree that's in a churchyard in Perthshire. There's the Waitrose up at Surbiton, another example of an instance, a particular place, and perhaps a street light out in the streets here that has a individual unique number on it. Then we can take these instances of individual physical things, which may be, let's say, physical or abstract, and we can group them together into classes with similar an ornamental planting, a park system. We may be thinking about trees, ornamental planting, ground cover, vegetation, and then there may be specific instances of these particular trees, for example. There are trees and particular instances of trees. So in the object model, we divide the world into classes, of which instances are the real world manifestations thereof. Oops. So, we have these general classes: trees, shops, bushes. Okay? Those classes in the object model are made up of two types of things. They are made up of attributes and behavior. Okay? So the attributes are, well, we're well familiar with attributes. A car is red, a car has a 1500 horsepower engine. The bank is an HSB, the building houses the HSBC bank, for example, has an address. So these attributes, so a group of objects, a class of objects can have a set of attributes, or an instance of objects, a set of attributes, which may be the atomic values that we're familiar with, a number, a bit of text, something like that. But they can also be much more complicated. So, for example, an attribute could be a list. An attribute could store spatial information, perhaps in a polygon. It may be links to an image or a sound, or it may in fact be another object. So you can have objects that are attributes of other objects. So attributes are relatively straightforward. Methods are sort of new. Methods are what an object can do, or what you can do with an object. They encode behavior. So the only way you should be able to interact with an object is through its methods. So there may be methods, for example, for updating attributes, but there may be methods that do much more complicated types of analysis or querying behavior. So that's it. Objects are made up of attributes and methods. Object classes are not standalone entities. We can define various relationships, just like we can define relationships in the relational model, between the various classes that we define. And we'll go into more detail about classes. So, for example, particularly, we can define a superclass subclass relationship. I'll explain these in detail in more full. We can also define the composition, and I'll explain that in more detail in due course, and the one we're familiar with, cardinality. So in the relational model, you can only really define cardinality, but we've got these other relationships that we can also define between objects. The classes that you choose, the attributes that you set to classes, and the methods that you can apply to classes, and the relationships between the classes together create what we could call a model or a view, or in computer science terminology, an ontology of the world. What is ontology? Big word, or not so big word, but it's philosophy again. Can't avoid these philosophers. It's defined as the philosophical study of the nature of reality and the components of which it is made. Contrast with epistemology. Epistemology is the study of how you go about doing scientific investigations and other types of investigations. Ontology is about splitting the world, nature, apart into parts, and what we call them and what the properties of these parts are. But in computer science, ontology, the word ontology, is generally used in a more specific sense to relate to a formal or defined in a computer model of reality. And that's what your classes and their relationships do. They are a formal model of how the world works. They provide a formal model of how the world works. So object classes and the relationships may be an example of a computer science formal ontology. there are many, many different ways of looking and cutting up the world into parts. So there is one world, as far as we know, but many different ways of views onto that world, onto that world. So for example, from the town planner, if we can take that, our example of the town centre, different people, different groups, different organisations will take different viewpoints onto the town centre. So the town planner may be interested in what businesses are occupying which buildings, which are residential, what's the mix of use, etc., etc. At what times of the day is the town quiet versus alive, etc., etc. The maintenance staff aren't interested in who's occupying which shops generally. They just want to know when to maintain the beds, how to maintain the beds, what the cost of maintaining the landscape, the townscape is. The marketeer may well be interested in empty properties, empty shops, turnovers, footfall, etc., etc. Whereas the health professional may be interested in things like, I don't know, curbs, places, dangerous places for, where people get run over, possibly the possibility of contracting disease from people, who knows. But the basic point being that there are different views that can be put onto the world itself. You cut the world up depending on what your problem is and who you are. So different groups of professionals will devise different ontologies, different class model, different sets of classes, different sets of relationships, etc., etc. So ontologies that ostensibly look at the same real world problem may differ in a variety of things. So they may differ in the set of named classes. Is the class called shop or is it called business? Have you got one? Is it called shop or is it called business? Is there a difference between shop and business? You may have one class for tree, one for bush, one for herb, or you may have one herb being just a small plant without any wood with no woody stalk, or maybe you have one class for vegetation that covers all of those and includes all those. So you could have some smaller classes, 3 small classes, or 1 big class. There is also how those classes are actually defined. So you may have the same name, business, in 2 different ontologies, 2 different computer models, but the definition of business is different in each one. So for example, or here it's shop. So we've got a class called shop. What is a shop? That may seem self-evident, but for example, are the stalls, the food stalls down in Kingston Town Centre, are they shops? What about these pop-up things that are very popular at the moment, popping up all over the place? Are those shops? What about online? So they may well have the same name, but have different definitions, have different coverages. Here's another one. What's the difference between a tree and a bush? Okay, so let's say we've got 2 different classes, one called tree and one called bush. And when does a bush become a tree? You laugh, but it's a serious question. Somebody has to deal with this, and you may have to deal with these kinds of questions at the time. You have to come with a definition. Is it based on height? Or is it based on species?
We had a conversation about this exactly, about trees and bushes.
Yeah, trees and bushes. I think I've mentioned it before, yeah. Okay, what's the difference between a tree and bush? And also the set of attributes recorded may be different in different models, and the methods may be different for different ones. Okay. So before we move on, let's just say why we're bothering with objects. Maybe this slide should have come at the end. Why bother? We've got the relational model, so why did anybody bother with object models and developing alternative models? Well, first of all, and I think it's in many ways it's raison d'etre, is that it provides a very powerful and importantly intuitive way of modeling data. We know we can take something in a computer, it's called the shop class, we know what a shop is in the real world. Whereas in the relational model, for example, what an entity is in the database may be spread across multiple tables. So it may not be, you don't get a clear mapping between things in the real world necessarily and how the data is organized in a relational database model, because the attributes of the object are spread across multiple tables, multiple attributes, and it has to be effectively reconstructed. So it's a very intuitive model. It's efficient in managing of code. So it's a good way of managing code, a good way to model code. And just like we don't want duplication in data, because then we have to update multiple copies, we've got the problem of maintaining integrity. We similarly don't want to duplicate code when we write code. We want one bit of code that we access to do the same job from wherever we are in our program. The next one is sort of one for next teaching block, because we haven't done coding yet. Objects can be used both in procedural and purely object-based programming. Now that won't mean anything to you, but next semester when we get into JavaScript objects and things like that, how to write, how objects work in programming, then you'll start to understand what the difference is between procedural and object-based programming is. But basically, objects can be used entirely within an object-based world, a completely object-based world, or you can use it in normal programming as well. So don't worry about the basics of that, but yeah. But objects have an upfront cost to develop. You've got to define, you've got to put in the effort to define them, to write the objects. Then you can actually start, once you've written your object code and defined your objects, then you actually start writing the program that's using the objects. So there is an upfront cost in defining and representing them. So to be honest, objects are not worth bothering with, I would say, for most basic scripting programs or developing object-based programs. Anyway, as I say, most of that relates to next year. A brief history of objects. Okay, they basically have a similar timeline to the relational model. They began in the late 1960s, almost exactly the time that COD was developing the relational model. So it's not that they're a reaction really particularly against the relational model, although they became that in due course. At the beginning, they were a way of dealing with a particular problem. And in 1967, the problem was of exploding ships. That just happened to be the environment in which the object model was developed. And I'm not going to go into the details of that, but basically, that's when it started in the late 60s. In the early 70s, small talk. So in the early 70s, by the early 70s, we started to get the first practical implementations of the object model. The first programming language was called Smalltalk, and it was developed by the RAG Xerox company, again, I believe in Menlo Park in California, where lots of things happened. And this was the operating system. This was a program, this is a programming language, Smalltalk, that was designed to run on an imaginary or a planned machine, which would have been the first notebook laptop computer, which was called the Dynabook. So the Dynabook only ever existed as this sketch, but they wrote the programming language that was meant to run on it. So Smalltalk was the first base sort of generally usable object language. And it included, so you can see in the 1960s, we just had instances of ships. Things get more complicated as we move through time, unsurprisingly. Okay, this may not, we'll get some more details on these words in due course. 1980s, C++ language came along. And that was when object-oriented program in general started to really take off. It became, you had a industry sort of very powerful, robust language which took on objects. And from the 1980s, I would say the object modeling prime has basically taken over the programming world. It's not that still people don't still write programs that are not object orientated now, but it's becoming very rare. And object programming, I would say, has become the norm since the 1980s in C++. In the 1990s, the programming language Java, which you may well have heard of, we probably installed it on your computer numerous times, updated it, was written. And Java, again, was one of these major stepping points that expanded the use of objects from basically computer nerds using C++. C++ is a very low-level programming language. I don't program in it. It's very fast, but it requires a lot of effort to program in it. Java is a much, what we call, higher level language. It's much quicker and easier to program things in, and that made it generally more accessible to a wider population of programmers. Interesting, the Java language is written in C++. So you have programming languages that are written in other programming languages. Okay, and it works as things written in Java as well. That means it gets worse, more and more sort of layers of the onion, so to speak. 1980s was also when we had the appearance of the object or object relational databases started to appear in the market. One of the most well-known then was called Small World. Have anybody heard of Small World? No. I'm not surprised. When I started my GIS world, the first GIS I ever used was Small World. It has a niche market, particularly in the utilities. So it's very strong on network modeling and things like that. So transport networks. I worked for the water department, so we were building water networks on it. So the object relational model started appearing in the 1980s. And then come the 2000s, a lot of the object concepts are now integrated or part of the sort of NoSQL movement. So we've got a gradual increase in complexity and availability of object-based software through time. All right, so this is the main part of the lecture. There are 5 object concepts. So this is from a theoretical perspective. Different languages, different databases implement the object model, these object concepts to a greater or lesser degree. But here we're getting the theoretical sort of 5 points which make an object model and an object model. Okay, the first one we pretty much met. Oh, right, maybe before I just start this, I'll just mention, okay, I've said programming languages and things like that. Objects, these objects, the object model can be implemented either in a program or as a way of storing data and retrieving data. The same model, you can use the same model in both cases. Basically, you could store an object in a database with its attributes. You could store the methods even in the database itself. Or you can extract them out and store them in memory and use them in a program. Okay, so it's the same model, can be applied both, to databases and permanent storage. Is that somebody trying to get in? And to, hello. And for dynamic programming in RAM memory. Okay, classes and instances. Okay, so we've met these already to a certain degree. So a class in an object or in the object model, a class is a template, blueprint or factory for making object instances. It's a thing that we define, it's a template, our class, then you say, give me a new instance of that class. Give me a new Ferrari, if only if it was that simple. So our class defines attributes and the methods of the class, and then we could create new instances from that class. Classes can be something as sort of a physically real as cars, or they can be more abstract entities. So, for example, in Visual Basic, all the graphical user things like buttons, labels, forms, checkboxes, these are all programmed and are all examples of objects in Visual Basic. So if we can go, I think we've highlighted button 1, highlight button 1, get up the properties, and you can see these on the right-hand side. These are the attributes of that button object. Okay, so it doesn't have to be Ferraris and cars and buildings. It can be bits of a form, things like that. So here's Ferrari. It's going to be cars for the moment, just because I inherited them, not because I've got any love of cars. In fact, quite the opposite. So here's class Ferrari. So what properties or attributes might we have of the Ferrari car? Okay, well, maybe a model number, a colour, an engine type, a value in pounds maybe, cost in pounds, how much fuel the fuel tank takes. So those might be some examples of the properties of that Ferrari. But what about the methods, the things that the Ferrari can do? Well, you can stop and start the engine with a key, with our virtual key. We can theoretically stop and start it. We should be able to accelerate or decelerate our car. Imagine we're in a sort of game here, game environment. We need something we can speed up, slow down. Not quite the same as starting and stopping, is it? Starting just turns the engine on and then one gets going. Maybe we've got a handbrake that we can take on and off to give us greater stability when we're stopped. Maybe we need to add fuel once in a while to keep it going, otherwise it's going to run out of fuel. And who knows, maybe we've got to play some groovy music at some time. But you can see you could write your list of properties, your list of methods, things your car can do, properties that your car has. I'm not going to tell you how we implement methods and things. I'll talk about that when we do JavaScript objects next year. So this is, as I say, purely theoretical. We're not going to see any code actually in this lecture. So the second thing we need to know about is relationships, and in particular, first of all, the inheritance relationships. And this is probably the most important relationship in object model. Basically, we can organize classes into what is called a class hierarchy, in which the subclasses inherit properties and methods from their superclasses. But first of all, just to make sure that we understand what a class hierarchy is, okay, so we've got Ferrari as a type of class, okay. Car, motorbike, and truck, these are three different classes, are all types of motor vehicle, which means that car, motorbike, and truck are subclasses of motor vehicle, and that motor vehicle is the superclass of truck, motorbike, and bike. Nothing like a diagram. So here's a diagram. Okay. So at the top of our hierarchy, we have a class, in this case called motor vehicle. So it includes all the possible motor vehicles that we can envisage. We have various types of motor vehicles, subclasses of motor vehicles. In this case, we've got car, motorbike, and truck. Okay, we could spend hours discussing what the appropriate subclasses of motor vehicle might be, but in this case, we've got these three. And in this case, we've got another subclass of class car, which in this case are class Ferrari and class Volkswagen. Okay? So we can see that motor vehicle is a superclass of these three. Car is a superclass of Ferrari, Volkswagen. These three are subclasses of car. Okay. As we go from from the superclasses to the subclasses, we are moving from the general to the specific. The class motor vehicle includes all attributes and methods that are common to all motor vehicles, be they a car, a truck, or a motorbike. It's a very general class. Car just contains methods and attributes, properties and methods related to the car, but it also gets the ones from motor vehicle. It inherits methods and attributes from motor vehicle. Similarly, motorbike has methods and attributes for a motorbike, but also inherits the ones from motor vehicle, and similarly down the hierarchy. So we move from general to specific. The other thing that's being highlighted on this diagram is the idea of abstract and insatiable, not insatiable, I'm sure it should be insatiable, not insatiable. That's insatiable, that's terrible. Yeah, as in being, you can create instances thereof. Instantiable is probably the correct word, instantiable. Okay, so what it is that some classes you can create instances from, others you can't. So the instantiable, it's not insatiable, instantiable, dear me, classes are only Ferrari and Volkswagen in this model. You only create a new Ferrari or a new Volkswagen. You cannot create abstract classes. So there's no such thing as a new car, because car is abstract. The idea of a car is abstract. There is no car called car or anything. You know, it's a level above, but in this case, the only classes that we can create instances of are further down here. So some classes you can create instances from, others you can't. So here's an actual practical example. Here's subclasses, remember, inherit attributes and methods from their superclass. So we have a class here, a superclass motor vehicle, has a vehicle ID field, a chassis number, and an owner. This is the inheritance relationship in UML. We'll meet that. So a truck is a type of motor vehicle. Truck has defined tachograph ID. Tachographs, in case you don't know, is those bits of paper in lorries that record how long people are driving for. So cars don't need tachographs, motorbikes don't need tachographs, but trucks do. And in this case, we've got a maximum load, so we don't overload our vehicle. I can instantiate, I've got the right word in here, that's better, a class for my truck. There's my truck, it's a fine vehicle. Don't you laugh at my truck. It's got a vehicle ID, it's got a chassis number, it's got an owner, it's got a tachograph ID, and it's got a maximum load of 500 grams. I've got all these attributes, 2 of which came from truck, 3 of which came from motor vehicle. That's inheritance. This could be a quick lecture, this. Composition. Composition is when an object is part of another object. So an object is made up from other objects and attributes. So, for example, here's our car. It's got a property colour, red. It's also got a property engine. Now, in a normal attribute, we just call that, we'd have the text or something describing what engine was in the car. But in the object model, that property can point to another object, in this case, an object of the type engine, which has properties cylinders, properties of pistons. So the composition relationship is that the property of an object is another object, basically. And in this case, each car can only have one engine. So it's a one-to-one relationship between engine class and the engine property in the car class in this case. But relationships don't have to be one-to-one between composition relationships. We may have a list of items or list of objects as one of our properties. So this is some situation where people kick balls around on a field. But so in this case, we've got groups, and then we've got countries in groups. So you could say that the countries within the groups, if these were objects, so the groups are, each group is an object, and then in this case, the members of that group, there are 4 members, which might be other objects. So you can have one-to-n component relationships as well as just one-to-one relationships. Polymorphism. So we've got objects, we've got classes, we've got object hierarchies. Polymorphism is the idea, the concept, as it says there, one interface, many behaviors. Okay. This is, so remember, we inherit down in a hierarchical relationship, yep? The subclasses inherit from their superclasses. But what happens when you've got, say, this huge hierarchy of objects, and just one of them, somewhere down lower in the hierarchy, has different behavior from everything else in your hierarchical structure? According to the inheritance rule, we couldn't specify the general behavior at the superclass level because not all the objects in the hierarchy inherit that relationship. If we did it, that would be what we would expect. Polymorphism, if a language, a system implements polymorphism, it allows you to overwrite the methods and properties defined by superclasses. Okay, example. And basically, what happens is that the method behavior or the property, what the property is, depends on the object class. So here we've got motor vehicle. Okay, most motor vehicles have 4 wheels. So if we want to calculate whether we're going to do a roll as we go round a corner on a racetrack or whatever, then we need to measure the stability. We need to decide, is it going to roll or is it not going to roll? So for the vast majority of vehicles, in this case cars, trucks, but we might have caravans, all the other types of 4-wheel vehicles there, they all perhaps share an algorithm that calculates cornering stability based on 4 wheels. And in our class hierarchy, we've just got one class, motorbike, which needs a different equation because it's only got 2 wheels. So what we can do is we could define, at a motor vehicle level, we can define a 4-wheeled cornering stability method, okay? And then that is inherited by all classes beneath it. But we need a different algorithm for the motorbike. So what we can do is define a new algorithm at the class motorcycle, in the class motorcycle, and this algorithm, what we call, overrides the one defined in the superclass. Okay? So it's an efficient way of just saying one of my subclasses, or this subclass, or this subtree of classes needs a different method to most of what's going on in the rest of our object hierarchy. So that's polymorphism. How the cornering is calculated depends on the class that the cornering's being calculated on. And that is overridden in this type subclasses and below that subclass because it's got the same method basically defined at the subclass level compared with the superclass. That's the concept of polymorphism. Now so some languages, programming languages, take this idea of polymorphism as to me to the extreme. So Visual Basic, in the .NET environment. VB, what's VB? Visual Basic is a programming language. The way I understand it, .NET is Microsoft's development environment for programming, in which you can which allows you to integrate programs and scripts written in lots of different languages, one of which is VB, but you could also write things in C, Java, many other different languages. It is the environment, or the .NET environment, is the environment in which you develop ArcGIS custom applications. So if you were to develop, say, have ArcGIS as your base GIS, but you wanted to develop a specific interface for perhaps a company, for people maybe answering the telephone and doing what they need to do when they answer the telephone, you would probably write it in ArcObjects in VB.NET or something like that, or in a JavaScript application. Anyway, doesn't really, the point being about VB.NET is that, and other interface-based approaches, is that you can only interact with the instances of your objects through what are called interfaces. You can't actually directly interact with the objects themselves. Okay, so here we've got a class motor vehicle. And motor vehicles can move, and perhaps they've got a direction and a velocity, two parameters that go into the move function. And we might have a method called move, which acts on the motor vehicle, for example, move whatever, 100 units, 45 degrees or something like that, from north or something like that. We also have a class here called animal. Animals almost move, but they move in different ways than cars do. So here's maybe this is a speed, who knows, but whatever. So you have a move function. Both can move at an angle, and both can move at a certain distance. But perhaps how they move or how they cross the terrain that they've got to cross depends on whether you've got legs or whether you've got wheels. In VB interface programming, you don't call the move method on the class animal or the move method on the class vehicle. You can't do that. You're not allowed to do that. What they make you do is create a new thing called an interface, a move interface, onto one of these objects, and then you've got one method, move BD, so you use the interface to interact with the class rather than directly working with the class itself. Now that is probably rather hard to get your head round, but it's sort of moving what it does is it's removing the user from the internal workings of the object. So all you need to know as a programmer is that you need to move, but you don't need to know any details about how you move. I don't like interface programming. I think it's a level of complexity. It's meant to simplify things, but I think it's a level of complexity that actually makes it more difficult to understand what you're doing in the first place. Anyway, just so that you know about that. Right, just before we finish, we'll take this we'll have a break. The last concept, important concept in object programming, is the concept of encapsulation, which is the idea, which is related to what I've just said, which is the idea that the details of the implementation of the object are hidden from the user. So here's a cat, you don't say. You stroke the cat and it purrs. You drag the string and it chases it. But we don't need to know what goes on inside, how the cat operates, for us to get it to purr. We just stroke it in theory to get it to purr. We pull the wool to get it to do the wool wrangling method. So it's the idea that you interact with the sort of outside of the object without needing to know what's going on inside it. That's the idea of encapsulation. It's also known or called information hiding. So it's the concept of separating the user from the details of how an object works. You don't need to know how it works to use it. And to be fully encapsulated, it needs for encapsulation, for a programming language or an object-based system, to say it supports encapsulation, requires these two things to be met. First, that the objects are fully described by the code, the class code that describes it, okay? We'll see class codes and things next semester, but basically all the code is in one place wrapped up into a nice, easy button. You don't have to have these external dependencies. Remember PostGIS. If you don't have the GEOS library, and if you don't have these other external dependencies properly configured, your spatial analysis and PostGIS won't work. So similar to that, everything has to be wrapped up in one piece of code in one place. You don't have to get external libraries and things like that. The other requirement is that the objects can only be interacted with through defined methods or interfaces. So either methods or interfaces. You can't go in and manually change the attribute in an instance of a object. The reality is in many programming languages you can do that, but this is kind of the ideal theoretical object model, not the dirty reality of how objects are actually implemented in various bits of code and programming languages. I don't think I'll bother with that. It's the idea of, hey, okay, well, we'll ignore that. You can look at that. All right, let's take a break, 10 minutes, and then we'll get on to UML and the object. Do you have any questions about the object model there? Well, I appreciate it's probably not easy to file away in your brain at the moment, but it will become, certainly when you get onto the programming side of things, it'll become a lot clearer what we mean, hopefully.